Hello viewers, in today's class we are going to solve one more important and conceptual problem from derivatives, right? So here we have a very interesting problem, and the problem goes like this. If x is equal to square root of 2 raised to cosec inverse t and y is equal to square root of 2 raised to sec inverse t, then we have to find the derivative of y with respect to x, right? So this is a case of parametric differentiation, and we have to obtain the value of the derivative of y with respect to x, right? So in parametric differentiation, what we do, we first find dx over dt, right? And then we find dy over dt, and dy over dx can be obtained by taking the quotient of dy over dt divided by dx over dt, right? So this is the method for parametric differentiation, because here y is a function of x, right? But x and y are separately given as a function of some other parameter, that is t, right? So dy over dx can be obtained by this expression, but here we'll use a slightly different method, right? So let us see. So here we will make use of the method of logarithms, right? So what we will do, we'll first take the square of both sides in this expression and as well as in this expression, right? So if we square both sides, see what we get. We get x square is equal to 2 raised to cosec inverse of t, right? And now let us take the log of both sides, right? So what we will get, we'll have log of x square, and here we have log of 2 raised to cosec inverse t, right? And similarly here also we'll take square of both sides, and what we will get, y square is equal to 2 raised to sec inverse t, right? And we'll take the log of both sides, so log y square is equal to log of 2 raised to sec inverse of t, right? So now let us first simplify this expression, then we will simplify this one, right? So here we have 2 log x, and here we have cosec inverse of t times log of 2, right? And similarly here we'll have 2 times of log y, and here we have sec inverse of t, and here we have log of 2, right? So here we have used an important result from a log, that is log a raised to b is equal to b log a, right? Okay, so let us denote this expression by equation 1, and here we can take it equation 2, right? So let us divide equation 2 by equation 1. So what we will get, we'll have, see, we have 2 log y divided by 2 log x, and here we have sec inverse of t log of 2 divided by cosec inverse t and log of 2, right? So 2 and 2 get cancelled here, here log 2 and log 2 get cancelled. So now we are left with log y over log x, and we have sec inverse t over cosec inverse t, right? Now let us add 1 to both sides, right? So if we add 1 to both sides, see what we will get. We'll have log y over log x. Here we have 1, and here we have sec inverse t divided by cosec inverse t plus 1, right? So now if we take the LCM in both sides, what we will get, see, we'll have log y plus log x, and then we have log x, and here we have sec inverse t plus cosec inverse t divided by cosec inverse t, right? So what we have done here, we have added 1 to the both sides, and we have simplified this expression, and we have got this one, right? So now let us use an important expression or result from inverse trigonometric function, right? So from inverse trigonometric functions, we know that uh, cosec inverse t plus sec inverse t, right, is equal to pi over 2, right? So this expression can be replaced by pi by 2. So here we have pi by 2, and in the denominator we have cosec inverse t, right? Okay, now log y plus log x can be written as, see, here log y plus log x can be written as log of x times y, due to the property of log, that is log a plus log b is equal to log of a times b, right? So we have log xy over log of x, and here we have pi over 2 divided by cosec inverse of t, right? Now let us observe this expression. See, this expression contains x, y and t, right? So now in the next step, what we will do, we'll try to express cosec inverse of t in terms of x, right? So see, from this equation we can write cosec inverse of t can be written as 2 log x divided by log of 2, right? So we can replace this cosec inverse t by this expression. So we have log of xy divided by log of x, and then we have pi by 2, and here we have 2 log x divided by log of 2, right? Okay, so now this log x and log x get cancelled, and here we have log of xy is equal to pi over 4. This 2 and this 2 get multiplied, and this log 2 can be taken to the numerator, right? So now we have this expression. Now we have to differentiate this expression in both sides, right? So we'll differentiate both sides with respect to x, and here we must note that pi by 4 log 2 is a constant, right? So this is a constant, and the derivative of this constant must be 0, right? So d by dx of log of xy is equal to 0, right? Because the derivative of this term, which is a constant, is 0, right? So now we have d by dx of log of xy is equal to 0. So the derivative of log of xy is 1 over xy, and then we have to differentiate this xy by chain rule, right? So now we can differentiate xy with respect to x. So we have 1 over xy, then x, the first function here will use the product rule. So x, then dy over dx, then we have the second function y, and the derivative of x is 1, and this is equal to 0. So multiplying this term with 0, that makes it 0. So we have x dy over dx plus y is equal to 0. So dy over dx, x times dy over dx is equal to minus y. So dy over dx is equal to minus y over x, right? So this is the final result for the derivative of y with respect to x. So dy over dx is equal to minus y over x. Now viewers, here let us take a second method to solve this problem, right? So in the second method, what we will do, see, we have x square is equal to 2 raised to cosec inverse t, and we have y square is equal to 2 raised to sec inverse t, right? Now in this second method, what we will do, will not take the logarithm of both sides, right? What we will do, will directly multiply these two equations side by side, right? So let us take this equation as 1, this equation as 2, right? So if we multiply 1 by 2 side by side, then we have x square times y square, and here we have 2 raised to cosec inverse of t times 2 times sec inverse 2 raised to sec inverse of t, right? So here we have xy whole square, and here we have 2 raised to cosec inverse of t plus sec inverse of t, right? Because the bases are same, so we can easily add the exponents, right? So here we have used x raised to m times x raised to n is equal to x raised to m plus n, right? So now from inverse trigonometric functions, cosec inverse t plus sec inverse t is equal to pi over 2, right? So we have xy whole square, and here we have 2 raised to pi over 2, right? So now let us differentiate both sides with respect to x, right? So what we will have, we'll have d by dx of xy whole square, and here we have d by dx of 2 raised to pi by 2, right? And see, 2 raised to pi by 2 is a constant, so the derivative is 0, right? So the derivative of 2 raised to pi by 2 is 0, and now we have d by dx of xy whole square is equal to 0, right? So now we can differentiate it. So we have 2 times of xy, and by chain rule we have d by dx of xy, right? And this is equal to 0, right? So now this term disappears here, because if we divide 0 by this term, we'll get 0. So we are left with d by dx of xy is equal to 0, and now we can use the product rule here. So this is the first function, this is the second one. So we have x, first function, derivative of second, then second, derivative of first, and this is equal to 0. So the derivative of x with respect to x is 1. So we have x dy over dx plus y times 1 is equal to 0. So we have x dy over dx is equal to minus y. So dy over dx is equal to minus y over x, right? So we see that again we have arrived at the same result, right? So this is how, by these two methods, we can solve this problem easily.